Okay, welcome all of you. Welcome back from the quiz. Again, today is all about extrema. So we're going to see highest and lowest points and how to figure all that out. But before we do that, let's go over the quiz and see how to do it. Okay, so here's your quiz. And let me do... Okay, so we have our quiz, and what we want to do is, want to suppose you need to paint. Okay. Oh, it should be a wall, but I don't think that's a problem. Okay, that is in the shape of an isosceles right triangle. You measure the base of the triangle to be, I was really tired, 4 meters long with an error of at most 0.002 meters. So we want to use differentials to approximate the propagated error for the area of the wall. So before we even get to the differentials, we need an equation. We need a formula for the area. And I tried to pick one that was pretty easy, but I never know what's going to be easy for you. So how do we find out the area of this wall if it's an isosceles right triangle? The hint is it's quite easy. So who knows how to find the area? Yeah, it's 1/2 the base times the height, but since it's an isosceles triangle, it's just 1/2 the base squared. Any questions on that? So let me just write that out. And I know you might want to call base B. I'm going to call it X because it feels more mathematical. So area, which I'll call Y, equals 1/2 X squared. Any questions on that? That was the first step. And again, you are responsible for knowing the very basics of geometry, which is area of a right triangle is 1/2 the base times the height. And isosceles means base and height are equal. Okay, so we want to use differentials to approximate the propagated error for the area of the wall. So what we have here, let me just remind you that dy is equal to y prime dx. Any questions on that formula that we had? And that was differentials. Okay, once we have that, then we just go and do it. So what's y prime? This is a really easy one.
X.
Yeah, so y prime is just x because the derivative of 1/2 x squared is just x. So we know that dy is x times dx, and then we plug in. And x is 4, and the dx is the error, which is 0.002. So what we can say is that dy is equal to, again, it's x times dx, and x is 4 times 0.002, which is equal to 0.008, just doing the arithmetic. Any questions on that? Okay, and that is the propagated error. Any questions at all so far? Okay, so then we want the maximum relative error. So who remembers what relative error is? Yeah, that's dy over y. Okay, so we need to find y, but y is pretty easy because y is 1/2 x squared and x is 4. So let's write that out. So the first thing is y equals 1/2 x squared, which equals 1/2 times 4 squared, which is 8. Any questions so far? So then if we want the relative error, we take dy and we divide by y, which is very easy. So what do you get, by the way, for the relative error? What do you get for the relative error?
.001.
Yeah, because dy was 0.008 divided by 8, because that was y. And that's just 0.001. Any questions so far? So far, so good? All right. Part C should be really easy if you got part B right. What do you have to do to get part C?
Times it by 100.
Yeah, multiply by 100%. And hopefully you don't need a calculator for that. I tried to do one on this one where you really don't need any calculator. I mean, hopefully you can do all these calculations without issue. So multiply by 100% and you get 0.1. So the percent error is equal to 0.001 times 100%, which is equal to 0.1%. Okay, and that is the percent error in the measurement of the area. Any questions at all on this quiz? Any questions? Okay, if there's no questions, let's move on and go to the webinar. Okay, and go to our table of contents. So are there any questions that you might have about anything? Could be the exam, could be homework, could be, I don't know. Any questions? Okay, if there's no questions, I think I'll go and talk about what we're doing in this section, the coming up section, and that is talking about Extrema. And I want to mention a few things. I'll do it by story. I'm not sure what you did over the weekend, but I did what I often do, and that is I went hiking, and I went to the top of Tahoe Mountain. Okay, now the top of Tahoe Mountain, I don't know, I'm sure you've seen Tahoe Mountain if you live in Tahoe. Whether you've hiked it, it's not that hard to hike, actually. But when you're at the top, whether you go left or right, you go down. Does that make sense? And no matter where you go, from the top of Tahoe Mountain, if you take one step, you go downwards. Okay, so kind of the way we want to think about that is an extrema, and it's a maximum, but is it the global maximum on Earth? What do you think?
No.
No. Now here's a tough question. As measured from the center of the Earth, okay, you said Tahoe Mountain's not the highest, but as measured from the center of the Earth, what is the global maximum on Earth? If you're measuring from the center of the Earth outwards, and you're going to be on Earth, and you want to hike to the very highest, measured from the center of the Earth, then is there a global maximum? Okay. Well, the equator's big. There's mountains, remember.
Everest.
Okay, so this is a trick question. Most people think it's Everest, and it's not. Okay, so let me show you. I popped this from NOAA, and NOAA's a science place, so they get it right. It's actually not Everest, it's Chimborazo. So if you ever want to climb to the highest mountain on Earth, measured from the center of the Earth, don't go to Everest. Go to the top of Mount Chimborazo. And that is the global maximum on Earth. Any questions on that? Okay, so the global maximum is there. Where's that? I think it says in here, doesn't it? Ecuador. So it's in Ecuador. I have not been there. Okay, but it's not even in terms of elevation, which is elevation is from the ocean, not from the center of Earth. It's not even close to Everest, but from the center of Earth, it's much higher. And that's, remember, the Earth is not a sphere. The Earth is, it's not flat either, by the way, but it's an ellipsoid. Okay, so you can pretty much, things have global maximum. By the way, is there a global minimum? Just on Earth.
Yes.
Okay, where is that? And the hint is it's not the Dead Sea in Israel. Okay. And water counts as surface. So you can't go, you know, I'm not talking about the surface of dirt, but water counts as surface. Anyone know? Turns out it's the North Pole. So the North Pole itself is the global minimum on Earth. Okay. So what I want to mention is global max and global min come up, they're important, and you want to think about them. And they come up in every subject. So what do economists interested in for global maximum? What do you think? If you're an economist, what might you be interested in to find the global maximum of something? Yeah, maximum profit is the biggie. Okay, there's some others too. Maximum revenue might be interesting too, but profit's number one. And so maximum is important, and minimum could be important also. Okay, but it comes up everywhere, max and min, in terms of applications. So again, for money, you want the most profit or the least cost, and that would be the global minimum. You know, if you're shopping and you want to get the best buy, then that is the global minimum. Any questions on that? Okay. How about in biology? What's important about the global maximum?
Carrying capacity. Max carrying capacity.
Carrying capacity could be important. Carrying capacity. Yeah, population. I like to think of it as the number of successful children that something has, because again, the global maximum in Darwinism will make that DNA the strongest. So pretty much every subject. How about in physics? Where does the global minimum come? Some of you might have had physics or chemistry. Physics and chemistry are kind of the same thing. No? So the global minimum, things tend to minimize energy. So a reaction will occur at the minimal energy. Okay. And electron orbital distance has something to do with that. It's very complex, by the way, just let you know that. And then maximum happens to, again, minimum and maximum are everywhere. So I want to let you know how important this particular section is, because it's used in every single science field. Okay. And a lot of non-science fields also. Okay. How about in structural engineering? What do you usually want to maximize? No, integrity. Okay, so integrity. So bridge integrity. So in other words, you want to make sure that you have a big, huge truck. It's not going to destroy your bridge if it goes over it. So you want to maximize the amount of weight that can go onto the bridge by looking at the different, structures that you have choices for your bridges. Any questions on this? So again, I just wanted to mention how important this particular section is. It comes up everywhere. So now that I've talked about it, we need to define it. And to let you know, I am not going to do the Earth example. It won't work for our definition. And that has to happen actually third quarter, not today. And why are we not ready to talk about mountains on Earth? The highest and lowest mountain on Earth kind of thing. This is important. And we will in third quarter. Anyone know?
Is it because the Earth is an oval and not actually a sphere, like a?
That does make it more complex, but that's not the reason. No, it's because if you want to talk about a location on Earth, because remember, you're looking at elevation as a function of location. And location is two variables, not one. Longitude and latitude, for example, is a typical way you measure location on Earth. And in our class, we are only looking at functions of one variable. Does that make sense? Okay. Doesn't mean you can't do it, or it doesn't mean it can't be done, I say. You can't do it, but it doesn't mean it can't be done. It just means that we're not ready yet. Yeah, so it has to do with the 3 dimensions versus 2 dimensions. So we're going to stick with 2 dimensions, which are also important. Okay. The physical dimensions are less important than like equations that have a single variable. So we want to say, what does it mean? What does it mean to be the absolute, or sometimes call it global, maximum? So let's write down as a definition. Any ideas? My guess is you all have the idea, like in the feel of it. Any ideas of what a global maximum would be? So let f of x be a function, then f of x has a global maximum at x equals a if, what does it mean? Okay, it's pretty easy. That's a hint. You don't need calculus, actually. Any ideas? If I don't see you jumping in, I'll tell you. F of A needs to be greater than F of B and often we actually will use greater than or equal to. For all B. And I guess technically in the domain of F. Any questions? Any questions on this definition? right? As soon as I write it down, it's obvious, right? You got to, if you're the max, that means you're bigger than everyone else. That's all this says. All right, the good news is there's the next definition. What do you think the accompanying definition is going to be of? I just defined the global maximum.
The minimum.
Yeah. And the nice thing is I can copy and paste. And I don't have to change a whole lot of anything. So let f of x be a function, then f of x has a global minimum. Two-letter change. At x equal a. And what changes?
F of a is less than or equal to f of b.
Exactly. The greater than or equal to becomes a less than or equal to. You got to be smaller than everyone if you're the global minimum, right? Any questions on that? Okay, and then it's exactly the same. And those are the definitions of the global max and the global min. Any questions on that? Okay, now things get interesting. And I think I want to do it with pictures because that helps. Okay, and often, by the way, when you talk about a global max or global min, you restrict the domain. You say between this value and this value. Sometimes it's negative infinity to infinity, but sometimes you say, well, what's the global minimum between 2 and 5? And that's the domain. So what you're doing is you're setting the domain, and that is what you're talking about. Any questions on that idea? Okay, so we can pop in some examples. So how about sine of x plus 2 times the cosine of x? Actually, let's go, yeah, that works. Okay, and let's say x, I'll do it this way, actually. It might be a pain, I have to go like there. There we go. And I'm gonna set the domain with Desmos. I'm gonna say x is between 0 and, just a minute, I need to look at this again. And 3. Okay, and I want to look at the global min and the global max. Any questions on the idea of what I want to do here? Okay, so where does it look like, just eyeballing it, where the global max might be? Yeah, it looks like 0.5. Okay, it looks like 0.5. And where does it look like the global minimum is? Again, we're not doing calculus. We're just taking a look at the picture and checking it out. Where do you think the global minimum is? Where do you think the lowest point on the graph is? At what value of x? Okay, 3 is outside the domain. Remember, we restricted the domain between 0 and 3. So 3.5 is outside the domain. Not 3, but 3.5 is outside the domain. So where's the global minimum? Between 0 and 3 is what we're looking at. Okay, negative 0.2 is outside the domain. You have to be between 0 and 3. Yeah, it looks more like 3. Okay, because over here at 3 is lower than everywhere else. Do you see that? But I want to emphasize something because these points are very different in terms of what's going on here. So 3 is a border. Okay, that's a border of the domain. Whereas 0.5 is not a border, but what's going on? What's going on with 0.5? What's special about it? And now think calculus. And in fact, if I zoom out, I think you might see it a little even better. Or if I change it a bit and go back to, let's say, -5. That's good enough. Then what do you see at 0.5? What's going on here in terms of calculus? Okay, it's continuous. The whole function is continuous. There's nothing special about it being continuous at 0.5 versus any other number. But what's special about 0.5 here? This is important, and you should all know this from calculus. What's happening at that point, calculus-wise? Right. What's the most important thing in calculus? Yeah, the derivative. And the derivative is 0. We got a horizontal tangent line at that point. Any questions on that? Okay, so notice that if you have a global extrema, there's really 2 different ways that can happen. Okay, actually there's 3, but this example gives you 2 of them. There'll be another one I'll show you too. So one of them is that it could just be on the boundary. And another is a derivative could be 0. Are there any other things that could happen for other functions where you could have a global max or a global min? Could something else happen? And if so, tell me what it is. Or do you always have to either have the derivative 0 or be on a boundary? What do you think? Yeah, you could have discontinuous, okay, but you could even have continuous and you could still have a problem. So we don't want to use the word continuous. But it's kind of the same feel. All right, let me give you the example. Yeah, not differentiable. So let me give you an example, very simple one, absolute value of x. Whoa, just there we go. Absolute value of x. And notice that if you take the absolute value of x between, say, I don't know, -2 and 2, then the global minimum is at 0. The derivative is not 0 there. There is no derivative at that point. Does that make sense? And that's pretty much the only thing that could happen. Those 3 different things. And we're going to spend some time talking about that. We'll have a formal theory, but I wanted to kind of give you a good visual feel of what's going on first. So calculus is important to decide if you have a maximum or minimum. And the other piece besides calculus is just looking at the left and the right, the beginning and the end. Any questions on that idea before we move on? Okay, now here comes the next question. Do you always have a global min and a global max? What do you think? Okay. All right. So if you don't always have it, What do you need to know that to be sure that you do have one? So I can give you an example. Again, I'll give you a Desmos example. They're really easy to do. So we can do something like, how about 1/x? Does it have a global max or a global min, say between -2 and 2? Yeah, it doesn't. What's going on here? What made it not happen compared to the other examples I showed you where they did have them? Any ideas? They're not touching. Okay, I like that idea of not touching. What do we use in, what's our calculus way of saying they don't touch? They're asymptotes. Okay, but it turns out you don't even have to have an asymptote. So for example, if we had something like, how about I don't know, it's always hard to do this. Oh, I know, let's go this way, I think it is. What if it was something like the absolute value of x? Actually, I think I have to do it this way. If x is less than 0, then it's the absolute value of x. But if x is greater than 0, actually, it's x is not equal to 0 is what I want. I wonder if it'll do this. No, I didn't like that. So I got to do x is less than 0. Then it's negative x. And if x is greater than 0, then it's x. But if x equals 0, it's 2. Does that have a global minimum?
Yes.
Okay, if you think yes, tell me what the minimum is.
0.
Okay, then tell me what value this function hits 0. What value of x gives you 0?
0.
No, at x equals 0, you get 2. That's what it says. Right? Because that's the last part. It says x equals 0, you get 2. The colon means you get, that's what it is. The function's 2.
I understand that now.
Yeah, so this one doesn't have a global minimum. Do you see that? It gets really close to 0, but it never hits 0. So if it had a global minimum, you could tell me what it is, and then I could always make something lower. Okay, you could say 0.01. Well, then I could say 0.001, and that's even smaller than I can get there. But you'll never get to a minimum. Okay, what's going on here? What kind of function is, what calculus-wise, what's the issue of this function? So what's the issue with this function? Unlike the last example, last one had an asymptote. This one doesn't have an asymptote. Yeah, it's not continuous. So that brings us to the big theorem. And that says, if you're continuous, then you're good. Okay, so if you have a continuous function on a closed domain is what we call it, then there's always a global maximum and there's always a global minimum. So let's write that out. Okay, and by the way, we're here, extreme value theorem. Maybe I'll put it here. And what it says is let f of x be continuous on AB. Then f of x has a global minimum and a global maximum at some value it could be more than one value between A and B on AB. Okay, you could try all you want to try and come up with, one that doesn't work that is actually continuous, and you won't find one. And it makes sense that if you're going to go from here to there, somewhere between here and there, your elevation is going to be the highest. And somewhere between here and there, your elevation is going to be the lowest. Okay, as soon as I ask that, it's obvious. Of course, there's going to be a point which you're the highest and a point which you're the lowest. Does that make sense? Okay, because at least in, I'm going to call it Newtonian physics, you can't jump. Okay, it may feel like you're jumping, but you're actually going in a continuous way. So that's true of many, many things that you get a continuous function. Okay, for all models, basically. Any questions on the extreme value theorem? Again, it's an important theorem. It's a useful theorem. And if you think you can prove this theorem, or even understand the proof of this theorem today, you're wrong. This is a brutal theorem when it comes to proving it. And I'm not going to because it's too hard for calculus. This is a senior level math kind of theorem. But it's pretty easy to look at graphs and say, yeah, it must be true. But to prove it is actually very difficult. So I'm not going to. Sound good? Which means you're not responsible for even vaguely understanding the proof. But you are responsible for knowing it's true, that if you have a continuous function between A and B, including A and B, then there's always a global max and a global min for that function. Any questions at all on this idea? Okay, does this tell you how to find it? Yeah, there's a very big difference between an existence theorem and a step-by-step on how-to theorem. And this is just an existence theorem. Okay, finding it could be very difficult sometimes. Any questions on the extreme value theorem? Okay, the next thing I want to do is do critical points. So critical points are, when you think about the word critical, those are kind of the important ones. And if you want to look at the values of X, where you have importance in this class, what things can be important? What things are critical for this class? And we've been talking about the last 10, 15 minutes or so. Yeah, it could be not continuous. Okay, I think someone said that earlier, but that's okay. Could be not continuous. What else could happen to be critical based on what we've been looking at? Not differentiable. Okay, which, by the way, not continuous is always not differentiable. Not the other way around, but always that way works. But there's another important thing going on when we're talking about extrema, max and min. Remember? It was our first example. All right, if you don't, I'll give you the definition and then you'll remember. So definition. And that is a value, let's say x equals a, is called a critical value. Sometimes called a critical point. I don't like that word much, but I'll put it in there because it's really the value, not the point. If either f of x is not continuous, sorry, not differentiable, at x equal a, or if it is differentiable, then f prime of a is 0. Because remember that if the derivative is 0, you got a chance of being the max or the min. That's what we're looking at, top of the hill, right? Or bottom of the valley. Let me put that in red because it's important. I'm going to put point in too because often they're called critical points, but I like value better. Any questions on this definition? No big deal? Okay. Do you think this is pretty easy to find the critical point values, by the way? Right? What do you have to do to find the critical values? Any thoughts? Kind of step-by-step process. Okay, so yeah, I'm going to say step 2. Step 1, I'm just going to do it in order of the definition. Step 1 is to say, when is it not differentiable? And that's usually pretty easy. Usually you get zeros in denominators or some weird thing, a 0 over 0 going on, maybe an absolute value. They're usually pretty easy to spot where it's not differentiable. Okay, step 2 is to take the derivative. And step 3 is to?
Set it to 0?
Yeah, set it to 0 and solve. What do you think the hardest of the 3 steps is?
Step 2, taking the derivative.
All right, let me give you an example and you might change your mind. Okay, let's suppose we had something like f of x is equal to x squared. I'll do something that's not too bad. How about plus sine of x? Piece of cake, right? Okay, first thing, by the way, where is it not differentiable? Any ideas? Don't see jumping in? Nowhere. This is a differentiable function. X squared is differentiable, sine of x is differentiable, right? Hopefully you know those derivatives in your sleep, right? Adding two differential functions is always differentiable. This is differentiable. Is that clear? Okay, so that's the first thing. I'm going to write one is f is differentiable everywhere. Okay, step two. What's step two?
Take a derivative of it.
Yeah, is that hard?
No.
I don't think so. I hope it's not hard for you. Otherwise, it won't go well for you Friday, by the way. Because this is supposed to be one of, this would be like too easy a question to put on a test. to say, find the derivative. Okay, and hopefully you all know that you just get 2x plus cosine of x. What's step three?
Take 2x plus cosine of x equal to 0.
Okay. Who knows how to solve that? And the answer is none of you. Step three is the hard step. Calculus is never hard. It's the algebra that's hard. Algebra is very hard here. You try to solve that, you'd be sitting for hours and not get anywhere, I promise you. Okay, this does not have an easy solution. Any questions on that? It could be approximated, and we'll have a whole section on how to approximate the solution to this. Not today, though. And that's called Newton's method. But again, you can get maybe as many decimals as you want, but you can't get the exact answer. Okay, any questions on this? Okay. This does have an answer, by the way. In fact, if we look at 2x plus cosine x, is it ever equal 0? Yeah, right here. At around negative 0.45. I'm sure you're all thinking that before I graphed it, but it's not exactly negative 0.45. Okay, that's just 2 decimal places of accuracy. So the point is that setting equals 0 could be hard. So I want to give you that big warning, is that is troublesome. But there are ways of approximating. One is graphing and visualizing it and saying good enough. Okay, let's do one that we can do. So for example, what if you had something like f of x actually I don't want fraction yet, f of x first equals, now fraction. How about 2x to the fourth plus 3x cubed minus 24x squared plus 12x all over x. Find the critical points. All right, I want to ask you something. what's wrong with doing this as a first step? Saying, well, I can cancel the x's all over. And I can just say, well, that's the same thing as 2x cubed plus 3x squared. Oops. Minus 24x plus 12. What's wrong with that? And then take a derivative set it equals 0. Because I just simplified first. Anything wrong with that? And the answer is yes. Tell me what's wrong. There's a big group of you here, so someone can probably tell me. It changes the derivative. Actually, that's not the problem. It's not quite the problem. I mean, it's a little bit, but very subtly. There's something glaringly wrong. Are these equal? Are these two functions, this guy and this guy, are they equal? I cancel the x's. Are they equal? What do you think? Okay, if they're not equal, why not? And the answer is they're equal everywhere except at x equals 0. So the problem is that what I did is I looked at a new function, this new f of x, which is the same as the old f of x, except at x equals 0. Because at x equals 0, the old f of x was undefined and not differentiable. So before we do the cancellation, just note x equals 0 is a critical point. Any questions? Any questions at all on noting that those are not the same functions because at x equals 0, they're different, but everywhere else they're the same. So the good news is once I've written down the note, then I can actually do the simplification and it's allowed. So you could do algebra as long as you note any critical points you might have lost because of discontinuities or non-differentiabilities. And in this case, we had a non-differentiability at x equals 0 that we lost by doing the algebra. So we just note it. And then we're okay because now they're equivalent and outside x equals 0, they're exactly the same. Okay, and that saves us a lot of headache because now we don't have to do quotient rule. And hopefully you all agree that the derivative of this new function, kind of f new of x, is a lot easier than the f old of x. So now we take the derivative. We did step 1, now we're on step 2. F prime of x is equal, I'm hoping you can all do this, what do you get? This should be easy. Yeah, 6x squared plus 6x minus 24. Any questions on that? All right, that was step 2. What's step 3?
Set that to 0.
Yep, set it equals 0. Okay. Okay, and by the way, this one I planned out. Unlike I planned it to be nice, and I also planned the x squared plus the sine of x to be evil. So, if I'm going to be asking you, to actually do something, I'm never going to give you evil. But if I'm displaying something and kind of showing you why it's not always nice, then I'll definitely show you evil stuff. So if it were an exam, probably be more like this one, if you actually have to do it. So if set equals 0, what can we do? First step. Now it's beginning algebra, maybe intermediate algebra, but it's beginning intermediate algebra.
Quadratic equation.
Nah, it's easier than that. God, there's something in common. What can we do? First step. Nice and simple.
Factor.
Yeah, or just, how about divide by 6? Isn't it screaming to get divided by 6? So we get x squared, and then plus x minus
-4.
Yep. So it's -4 equals 0. I planned it wrong. I had a typo at the very beginning, but it'll still be not too terrible. But it's not as good as it was supposed to be. Okay, this one doesn't factor, unfortunately. That was supposed to be double that, but it wasn't. Okay. So instead, we can use a quadratic formula, which still isn't that bad. X is equal to good old fraction, -1 plus or minus the square root of b squared. That's 1 minus 4ac, which is plus 16, all over 2. So how many critical points do we have? How many critical points? It's not a trick question.
2.
Well, maybe it is a trick question because it's not 2. 3. We have a critical point at 0. We have a critical point at -1 plus the square root of 17 over 2. And we have a critical point at -1 minus the square root of 17 over 2. That's 3 critical points. Is that totally clear? Okay, so there's 3 critical points. Okay, and those are the things that you're most interested in. Any questions at all on the idea of finding critical points, the 3-step process? Any questions?
Why is x equals 0 as a critical point on the front, right before we did step?
Because if we look at this original function, what happens if x is equal 0?
It's undefined.
Exactly. And undefined means not differentiable.
Understand.
Yeah. And not differentiable was number 1 for looking at critical points. Okay. And then if you look at the function, it is differentiable everywhere else. 0 is the only issue, right? Because whenever you have a rational function, only the denominator equals 0 is the only issues. Okay, so we now understand, hopefully, let's go through what we've got now, is we understand what an absolute extrema is. We understand the extreme value theorem. We understand what a critical point is and the 3-step process on finding the critical points. Now it's time to talk about, instead of the global extrema or the global maximum min, Now it's time to talk about the local max and min. Local max and min is often more important because, for example, if you're hiking or something, you don't care about, Mount, whatever that name was, Tomor or something, Chimborazo, right? You care about the highest point in your little area, okay? The high points, okay? All the cool places to go. So Mount Talak, Friel Peak, those are the places you care about, not Chimborazo or something. You care about our little mountains that you can go to because those are our local, maximum. And similarly, if you often care about the local minimum, okay, they tend to be really, really important, okay, and needed. Any questions on that idea first before I define it? Okay, so now it's defining. Let's define the local max and the local min. It turns out they're a little harder to define than the global, but they're doable. So let's do the following. Let f of x be a function then f of x has a local extrema. I'm going to write maximum, and then I'll define minimum in a bit too. If, okay, so what does it mean to be a local maximum? Again, my guess is that you all got it in your head that, if you're like hiking or something, you know what it means to be, on a local top. Okay. Hopefully you know that. But what does it mean mathematically? Okay. Oh, it has a local maximum. Let me put it somewhere at x equals a. Okay, right. So the idea is a limited range. What does that mean, limited range? And I don't expect you to come up with the answer because it's theoretical and it's going to bring back some memories of a while back in this class. Okay, so we have a local maximum at x equals a if there exists an epsilon greater than 0 such that and now we write down the maximum equation, f of x, or f of a, is greater than f of b. And actually, I should write greater than or equal to, because equals okay. It's greater than or equal to f of b for all b such that the absolute value of a minus b is less than epsilon. So it's actually hard to define without getting fancy like this. And this is the definition. Let's make this good old red because it's important. So you need to be the biggest of your local neighbors. And the definition of being a neighbor is within epsilon, for some epsilon, even if it's really little. That's okay. And it has to be a positive epsilon. And then the nice thing is I could do local minimum with a copy and paste. It's exactly the same. Oops, I think I missed. There we go. It's exactly the same, except maximum becomes minimum. And the greater than becomes a less than. So again, a maximum means you're the highest of your neighbors, and a minimum means you're the lowest of your neighbors. Any questions on that? Any questions? Okay, now something I mentioned before. So this is the definition. And it's pretty easy, I think, to kind of picture it in your head. Using it's a little harder, but I'll show you it's not too bad because of a great mathematician named Fermat. Okay, by the way, have you heard of Fermat's last theorem? Have you heard of that theorem, Fermat's last theorem? No one's heard of it? About right triangles? Not right triangles. It says a to the n plus b to the n equals c to the n. Doesn't have any non-trivial solutions for n greater than 2. It is, in my lifetime, and I'm an old guy, it's the most famously proved theorem. And it happened, I think, right after I was in grad school. I was out of grad school, right? My first year teaching, my regular teaching job. It was a biggie. So, but this is not going to be his last theorem. This was one of his first theorems. So let me give you Fermat's theorem, but not the last theorem. I'm going to write not last. He didn't call it not last because he didn't know. Theorem. Okay, and it's what I talked about at the very beginning. If you find a point and it has a max or a min, then what do you think you know about that point? Hint, think calculus. If it's a local max or a local min, so let f of x be a function, then f of x actually, let's make it prettier. Then if f of x has a relative, by the way, relative local means exactly the same thing. Extrema, and extrema means max or min. Then, what do we know? Oh, sorry, at x equals a. Then, what do we know? It's what I mentioned at the very beginning, first 10 minutes. F of x has a critical point at x equals a. So a is a critical value for f. So it means that if we're going to look for the relative extrema, the relative max or relative minimum, then we do the 3-step process. We find the points at which it's not differentiable. And then we go ahead and we take a derivative. We set the derivative equals 0. And we look at those points. Okay, now based on this theorem, does that mean that if it has a critical point at, say, x equals 10, then f of 10 is either a local max or a local min? Can you say that? What do you think? Any ideas? Or let's go x equal 1 just to make it even easier to type. I don't see y'all jumping in. But let me give you an example. Okay, if you look at x minus 1 cubed, do you have a max, a relative max or relative min there? What do you think? Are you at the top or the bottom of the mountain or neither? Right there. I don't see y'all jumping in. Yeah, neither. Okay, so having a critical point does not mean you have a max or a min. But having a max or min means you have a critical point. So it only goes in one direction. On the other hand, if I made it 4th power, whoops, that was 34th. 4th power, there we go. Then you actually do have a minimum. That is the minimum value. Or if you make it the 2nd power, definitely a minimum value. Okay, if you pop a negative in front of it, now it's a maximum, relative maximum. So you may get a max, you may get a min, you also may get neither. But if you have a max or min, you know you have a critical point. Any questions on Fermat's theorem? Okay. This one is provable, but I think I'm not going to because it's really messy. So I think you'll be happy that I'm not proving. It's in the book if you really want to look at it. But I don't think we need to. And by the way, Fermat's last theorem, that was proven, about 30 years ago or so, maybe 27 years ago. And I did read the proof of that and understood it. It was about 300 pages long and brutal. It was definitely in my area though. So Fermat's a pretty important mathematician. Any questions on Fermat's not last theorem? Okay, let's just do some examples. So find the possible relative extrema for f of x equal x minus 2 times the sine of x. Okay, well, what's the first thing? What's step 1? What's step 1? Hopefully y'all know what is the first step. Step 2 is find the derivative. What's step 1? Yeah, determine differentiability, and x minus 2 sine x is differentiable everywhere. There's no issues. Step 2 is to find the derivative. And you should all know how to find the derivative of this. So what is f prime of x? It's supposed to be easy. You got part of it, Bruno. It's the derivative of x is 1. And then minus 2 cosine x. Any questions on that? Okay, what's next? What's step 3? What's step 3 for finding the relative extrema? Yeah, we set it equal to 0. So we have 1 minus 2 cosine x equals 0. And we solve. So now we can add 2 cosine x to both sides, divide by 2, and switch. And we get the cosine of x equals a half. When is the cosine of x equal a half? When is the cosine x equals a half? So you're supposed to remember your trig. Cosine of x is a half at pi over 3. Good. Anywhere else? How about negative pi over 3? Anywhere else? So plus or minus pi over 3. Yeah, 5 pi over 3. I'm going to call it plus or minus 5 pi over 3 because that's going to be easier to type. But then we're talking about a cosine function. So it's going to be plus 2k pi. There's actually an infinite number of relative extrema, points at which f has a relative extrema. Any questions on this example? I do want to let you know this is step 3. There's going to be a step 4, but not for this section. Because what we just did is we said these are the possibilities where you might have a max or you might have a minimum for a relative max or relative min. But that kind of leads us going, well, I want to know more. Which is it? Is it the max or min? If you want to maximize profit and you're not sure if you maximized or minimized, you could have a disaster if you choose the minimum by mistake. So we don't know how to do that today, but we'll get that right after the exam, I believe is when we're doing it. So that's a week from today. So we'll learn how to find where is it a max and where is it a min instead of where might it be a max and where might it be a min. And that'll be something different. There's 2 ways, first derivative test and second derivative test. Okay, so that's pretty much everything. We're at the time, just about within a minute. And let me end the recording.